Good morning, students. On behalf of Animal Institute of Technology, I welcome you all to the pre-runner gate class. In today's class, we are going to discuss about PN junction diode and Zener diode. Move on to the introduction of PN junction diode. First of all, we have to know what is junction. Junction is nothing but two dissimilar material will form the junction. Here we have P and N junction diode. P-type material and N-type material will join together to form a junction. So that is called as PN junction diode. What is PN junction diode? A PN junction is a boundary or interface between two types of semiconductor materials, P-type and N-type. Inside, a single crystal of semiconductor will be placed. It is created by doping. Doping is nothing but adding impurities to improve the concentration of the diode. So I said in the introduction itself, a junction is formed by the two dissimilar metals. So here we have P-type material and N-type material of the semiconductor will form a junction that is called as the PN junction diode. So it has been emphasized by adding impurities to create a PN junction diode. So this is the symbol of the PN junction diode. So this is the electrical symbol. Here the triangle symbol will indicates the direction of the flow of current. So this will be the negative terminal and this will be the positive terminal. So we have P-type material and N-type material. In between these two regions, we have a small empty region. So this is called as the insulated region. So here, this is the depletion layer. It has been formed as an insulator between the P-type material and the N-type material. So insulator will not conduct the current. And this P-type material and N-type material, the flow of charge carriers will tend to conduct the current. How the depletion layer is being formed? The excess electrons in the N region, on provided with the biasing supply, it will cross to the junction and combine with the excess holes in the P region. So in P-type material, it will be created with the holes, and N-type material, the electrons will be created. So when a biasing voltage will be provided to this P-type and N-type material, the electrons from the N-type material will cross over the depletion layer to combine with the holes. N region will be losing its electron. That's why it becomes negatively charged. Whereas the P region will accept the electrons from the N region, it will becomes negatively charged. So in N region, electrons will be moved from N region to the P region. So there is a loss of electrons in this N-type material because as the electron number is being reduced, it has been moved to the P-type material. That's why this N-type material will be negatively charged. Whereas in P-type material, it gains an electron from the N-type material. So that's why it is called as positively charged. At one point, the migratory of this electrons to the holes, that action will be stopped. And additional electrons from the N region are repelled by the net negative charge of the P region. Similarly, an additional holes from the P region are repelled by the net positive charge of the N region. Then what will be the net result? A creation of thin layer of each side of the junction, which is depleted in the sense it is emptied. There is no charge carriers. So emptied of the mobile charge carriers. This is known as depletion layer. So the thickness of the depletion layer will be in the order of 10 to the power minus 6 meter. Depletion layer is nothing but it's an empty region without any charge carriers. The depletion layer contains no free and mobile charge carriers, but only fixed and immobile ions. Its width depends upon the doping level. At the introductory part itself, I said doping is nothing but adding an impurities to the P-type and N-type material to improve the concentration of the charge carriers. So the depletion layer width will depends upon the how much the concentration of the doping has been evolved. With that only this depletion layer width can increase or decrease. If the charge carriers have been heavily doped with an impurities, then the depletion layer will be the thickness will be very very thin. If it is lightly doped, that is, if we had only very small number of impurities to improve the concentration, then the depletion layer region will be thicker region. So the depletion region, it has only immobile ions, it does not have any charge carriers. Then imagine if we add more number of impurities to improve the concentration, so the mobile charge carriers will be gain its concentration, so to conduct the flow of current. So since the depletion layer region will be very very thin, if it is being lightly doped, then the depletion layer will be consisting of thicker layer, and it does not provide any charge carrier, free charge carriers to the conduct the flow of current. Next, we move on to the potential barrier. The electrons in the N region has to climb the potential hill in order to reach the P region. We saw that that is depletion layer in between the P-type material and N-type material. When a bias is being provided, the charge carriers from the N-type material, that is free electrons, it will tend to move to the P region to combine with the holes. But in between, and depletion layer is being provided. The depletion layer is also called as a potential barrier. It has to climb the potential barrier to reach the P region. When the electrons are tried to cross from the N region to P region, it will experiencing a retarding field of the battery, and therefore it gets repelled. Similarly, it will be happen for the holes from the P region also. So the potential thus produced are called as the potential barrier. For the typical value has been given for the germanium and silicon semiconductor. For germanium, the potential barrier voltage will be 0.3 volt, and for silicon it is 0.7 volt. PN junction can basically work in two modes. When a battery is being connected to the diode, it is called as the forward bias mode. That is, positive terminal is being connected to P region and negative terminal is being connected to the N region. Whereas in reverse bias, so it's just contradictory to the forward bias, reverse to the forward bias. There in forward bias, we have connected positive terminal with the P region, and negative terminal of the battery is being connected to the N region. Here, negative terminal of the battery is being connected to the P region, and positive terminal of the battery is being connected to the N region. Forward bias PN junction. So what is forward bias? When the positive terminal of the battery is being connected to the P region and negative terminal of the battery is being connected to the N region. So under forward biased PN junction, the PN junction will forces the majority charge carriers to move across the junction. So automatically it will decreases the width of the depletion layer. So already I said when the doping concentration will be very very high, the depletion layer thickness will be very thin. Once the junction is crossed, a number of electrons and the holes will recombine. For each hole in the P section, it has to combine with an electron from the N section. A covalent bond will breaks and an electron is liberated, which enters the positive terminal, thus creating an electron hole pair. You just make a note of this. For each hole in the P section, it has to combine with an electron from the N section. A covalent bond will breaks up Next, we move on to the reverse bias PN junction. If the positive terminal of the battery is being connected to the N-type material and negative terminal of the battery is being connected to the P-type material, this is called as the reverse bias junction. So the free electrons and free holes are being attracted back towards to the battery, hence the back from the depletion layer. So the depletion layer will grows up. Thus, a reverse bias PN junction diode does not conduct any current because of the minority charge carriers, as the potential depletion layer will be very, very thick. Thus, the PN junction diode allows the electrons flow only when the P is being positive. This property is being used for the conversion of AC to DC, which is called as a rectification. So rectification is nothing but the process of converting the alternating current into the direct current. For that property, this PN junction forward bias condition has been used. So this is the VA characteristics of PN junction diode under a forward bias condition and reverse bias condition. So this linear graph will shows the under forward bias conditions when the positive terminal of the battery is being connected to the P-type material and negative terminal of the battery is being connected to the N-type material, the current will grows linearly. Under reverse bias condition, so the flow of current will get stopped, so it will be flows in the negative graph, so negative directions. Next, move on to the advantages and disadvantages of this PN junction diode. First, we'll see the advantages. So there is no filament that has been required to form this PN junction diode. It occupies very lesser space and it can withstand a long lifetime. Next, move on to the applications. It can be used as a rectifier to convert AC into DC. That is the primary application of this PN junction diode. And it can also used as a switch in computer circuits. It can be used as a detector in radios to detect the audio signals. It also used as an LED to emit different colors. LED is nothing but light emitting diode. So to emit different colors, this PN junction diode can be used as an LED. So that's the introductory part of this PN junction diode. Next, we will move on to the gate practice problems. Now look upon the first problem. Here, the diode circuit has been given. So the diodes and capacitors in the circuit shown are ideal. The voltage across the diode D1 is. So here they have implemented with the circuit diagram with two diodes D1 and D2. And we have the capacitors. They are asking to find the voltage across the diode D1. They have given the options, 4 options. First one is cos of omega t minus 1. Second is sin omega t. Third is 1 minus cos omega t. And fourth one is 1 minus sin omega t. What is the solution? What is the voltage across this diode D1? We have to find out. So the voltage V of t, the input voltage they have given us cos omega t. So it is given data in the circuit diagram. We have to find the voltage across the D1. So the diodes and capacitors are ideal. When the positive cycle of the input is applied diode, D1 is forward biased and D2 is reverse biased. D2 is reverse biased because now see in the diagram, this is the input voltage cos omega t, negative terminal and positive terminal. The positive has been connected to the anode terminal of the diode. So it is being under forward bias condition. So we clearly know that under forward bias, the majority charge carriers will tend to flow the flow of current. So the current value will be increased. When the positive cycle of the input is applied, diode D1 is forward biased and D2 is reverse biased. Capacitor C1 will be charges to the maximum voltage. Here it is 1 volt. When the negative cycle of the input comes, D1 is reverse biased, so replaced by open circuit. It will not conduct any current. So here note that D1 is reverse biased forever and can be replaced as a open switch. Open switch. So in this circuit, C1 and D1 will form a clamper circuit while D2 and C2 will form a peak detector. So this cascaded circuit acts as a peak-to-peak detector. So the correct answer option is cos of omega t minus 1. So cos of omega t minus 1 is the entire voltage applied across the diode D1. Because the capacitor will be tend to charge to the maximum voltage of 1 volt and the input voltage will be the cos omega t. Okay, so under forward bias condition, the positive terminal of the input has been connected to the positive anode terminal of the diode D1, and then D2 will be in the reverse bias condition. So D1 is being reverse biased forever, D2 is reverse biased forever, and it can be replaced as a switch. This is the open switch. So in this part, the current will not tend to flow. As it is being reverse biased, the current will not tend to flow in this region. So the correct option for this is cos omega t minus 1 is the entire voltage applied across the diode D1. Next, we move on to the next problem. The IV characteristics of the diode in the circuit is given below are. So for this circuit, the current voltage relationship characteristics has been given as I is equal to V minus 0.7 divided by 500 A, where V is greater than or equal to 0.7 volt, 0 ampere for V is greater than or equal to 0.7 volt. So the current in the circuit is, options are 10 milliampere, 9.3 milliampere, 6.67 milliampere, and 6.2 milliampere. As per the given IV characteristics, I is equal to V minus 0.7 divided by 500 ampere for voltage greater than or equal to 0.7 volt. From the given circuit, V is equal to, here this is the entire voltage, so 10 volt minus 1000 I, the current flowing between, so the entire voltage, so V is equal to 10 volt minus 1000 into I. So from the equations 1 and 2, you just eliminate V on both the sides. So I is equal to 10 minus 1000 I minus 0.7 divided by 500. So which is equal to 9.3 by 500 minus 2I. So this minus 2A when it comes to the LHS side, it will become 3I. So 3I is equal to 9.3 divided by 500, or I is equal to 3.1 divided by 500 minus 6.2 milliampere. So here the option is, option D is the correct answer, 6.2 milliampere. Next. In the circuit shown below, the knee current of the ideal Zener diode is 10 milliampere. To maintain 5 voltage across R1, the minimum value of RL in ohm and the minimum power rating of the Zener diode in milliwatt respectively are. So the knee current of the Zener diode given data is 10 milliampere. Knee current of Zener is the maximum current that should flow through the diode for proper Zener action. The Zener has been given with the voltage of 5 volt. Vz is equal to 5 volt. Find minimum RL and diode power rating. The minimum value of RL means the load current is maximum, I max. So VRL is equal to I max into R minimum. From this, R minimum is equal to R is equal to V by I. So VRL divided by IL max. So VRL is given as 5 divided by IL max. This is the equation 1. Now I is equal to IZK plus IL max. IL max is equal to I minus IZK. So here they have given us 50 minus 10, it is 40 milliampere. From this, R min is equal to 5 divided by 40 into 10 power minus 3, which is equal to 5000 by 40, equal to 500 by 4, equal to 125 ohms. So the minimum power rating of Zener diode is, it will be decided by the maximum current in Zener. Pz is equal to Vz into Iz max, which is equal to 5 into 50 milliampere, which is equal to 250 milliampere. So the option B is the correct answer. Next. A voltage 1000 sin omega t volt is applied across YZ terminal. Assuming ideal diodes, the voltage measured across Wx in volts. So voltage applied across Y minus Z terminal V1 equal to 1000 sin omega t. Diodes are assumed ideal here. So for positive cycle of the input, all 4 diodes are reverse biased. So VW minus Vx is equal to 0 or VWx is equal to 0. For negative cycle of the input, all the diodes are forward biased, that is short circuited. VWx is equal to VW minus Vx equal to 0. So VWx is 0 for all the times. So option D is the correct answer. It is 0 for all the times. Next, the figure shows a half wave rectifier. The diode D is ideal. The average steady state current in amperes through the diode is approximately. So the figure has been employed with one single diode. It's half wave rectifier circuit. Input signal is given as 10 sin omega t. Frequency is given as 50 hertz. Period of the waveform time is equal to inverse of the frequency. So t is equal to 1 by f equal to 1 by 50, 20 milliseconds. Time constant equal to RC. R is given as 100 ohm into capacitor value is given as 4 millifarad. So 4 into 10 power minus 3. So the time constant RC value is 400 millisecond. Here RC is 400 millisecond. It is greater than, very greater than that of time. So thus the voltage across the resistor can be approximated to 10 volt. So the current through the diode is ID of DC equal to 10 volt divided by 100, which is equal to 0.1 ampere. This circuit is also sometimes called half wave peak detector. In AM receive, it is used to detect envelope of the AM wave. So the correct answer will be the 0.1 ampere. Next, two silicon diodes with a forward voltage drop of 0.7 volt are used in the circuit. It has shown in the figure. The range of the input voltage for which the output voltage V0 is equal to Vi is. The given data is forward voltage drop of the silicon diode is 0.7 volt. Find the range of the Vi for which output voltage V0 is equal to Vi. Let us see the D2 branch of the diode. D2 will be forward biased when Va is greater than 0.7 plus 2, which is equal to 2.7 volt. D2 will be reverse biased when Va is less than 2.7 volt. Similarly, see the branch of D1. D1 will be forward biased when V1 is less than -1 minus 0.7 equal to 1.7 volt. D1 will be reverse biased when Vy is greater than minus 1.7 volt. When both the diodes will be reverse biased, then V0 is equal to Vin. Thus, it will happen when D2 is reverse biased when Vi is less than 2.7 volt and D1 is reverse biased when Vi is greater than minus 1.7 volt. So the range will be minus 1.7 volt less than Vi less than 2.7 volt. Option D is the correct answer. For the circuit with ideal diode shown in the figure, the shape of the output for the given sine wave input will be. So for positive off cycle of the input, D1 and D2 are on, V out equal to minus V in. For negative off cycle, D1 and D2 are off, V out equal to 0 volt. So the option C will be the correct answer. So for negative cycle, D1 and D2 will be in the off state. So option C will be the correct answer. Next. In the circuit shown below, the Zener diode is ideal and Zener voltage is 6 volt. The output voltage V0 is Zener voltage equal to 6 volt. Zener diode is reverse biased during its operation. Here with the applied voltage, the voltage across the Zener diode is V0 is equal to R1 divided by R1 plus R2. So 1 kilo ohm divided by 1K plus 1K. So into 10 volt, which is equal to 5 volt. Diode will be reverse biased but not in the Zener region, so open circuited. Next, if the circuit shown, so the answer will be V naught equal to 5 volt. If the circuit shown as to function as a clamping circuit, then which one of the following conditions should be satisfied for the sinusoidal signal of the period t? The circuit as being function as a clamping circuit, we have to identify the condition for which condition it has to satisfy for the sinusoidal signal of period of t. The circuit is a negative clamper. The present circuit has a load resistor connected in shunt mode. When diode is off, the capacitor discharges through the resistor R. The output falls exponentially with the time constant RC to avoid the discharge of the capacitor significantly. RC is very, very greater than T, but T is the time period of the sinusoidal waveform applied to the given circuit. So the option D will be the correct answer here. Next, the diode in the circuit given below has V1 equal to 0.7 volt, but ideal. Otherwise, the current in milliampere in the 4 kilo ohm resistor is. The diode in the circuit given below has V1 is equal to 0.7 volt, but ideal. Otherwise, the current in the 4 kilo ohm resistor is. We have to identify the current flowing across this 4 kilo ohm resistor. So the given circuit is a bridge rectifier circuit. So here we have the 2 into 6, which is equal to 3, 4 into 3. It is 12 equal to 12. So bridges gets balanced. So no current through the 1 kilo ohm resistor. In between this, there is no flow of current in between 1 kilo ohm resistor. Now current through the 4 kilo ohm resistor will be I is equal to 9 divided by 9 plus 6 into 1 milliampere. So 9 divided by 9 plus 6 into 1 milliampere, which is equal to 9 by 15 milliampere, equal to 0.6 milliampere. So 0.6 milliampere is the correct answer. Next, we move on to some other practice questions of this PN junction diode and the Zener diode. Look upon the question. In a forward biased PN junction diode, the sequence of events that describes the mechanism of current flow is an injection and subsequent diffusion and recombination of minority carriers. B is injection and subsequent generation of minority carriers. And option C is extraction and subsequent diffusion and generation of minority carriers. And D is extraction and subsequent drift and recombination of minority carriers. So what is the question? In a forward biased PN junction diode, the sequence of event that describes the mechanism of current flow is. So the correct answer is injection and subsequent diffusion and recombination of the minority carriers. In a forward bias condition, you know that positive terminal of the battery is being connected to the anode terminal of the diode. Negative terminal of the battery is being connected to the cathode terminal of the diode. So the description of to show the mechanism of current flow in the forward bias PN junction diode is it is an injection and subsequent diffusion as well as recombination of the minority carriers from the N terminal to the P terminal to the N terminal. Next, what is the efficiency of the half wave rectifier? In half wave rectifier, it will be consisting with one diode. So in that, during positive cycle only, it has to conduct the current. So the efficiency of the half wave rectifier will be 40.6%. What is the value of leakage current in the reverse bias condition? The value of leakage current in reverse bias condition will be in the 1 microampere. So in reverse bias, negative terminal has been connected to the anode terminal of the diode and positive terminal has been connected to the cathode terminal of the diode. So in the reverse bias condition, the flow of current will be drastically reduced to the 1 microampere. In Zener diode, Zener breakdown will occur at greater than 6 volt, less than 6 volt, and 6 volt, and last option is 0. So Zener breakdown will occur at the less than 6 volt region. When a PN junction is reverse biased, holes and electrons will tend to concentrate towards the junction. The barrier tend to break down. Holes and electron tend to move away from the junction. So the correct answer is holes and electron tend to move away from the junction, because in reverse bias there is no flow of current, there is no flow of charge carriers from N terminal to the P terminal, P terminal to the N terminal. That is electron to recombine with the holes and holes to recombine with the electrons. There is no such activity takes place because the potential depletion layer width will be very thick in reverse bias condition. So there is no chance of concentrating or combining the charge carriers will not happen, as well as the barrier will not tend to break down. So the correct answers will be holes and electrons will tend to move away from the junction. That will lead to the not to conduct the flow of current. Next. During the formation of PN junction diode, electron diffuses from N to P type, P side. A holes will diffuses from P to N side. A hole diffuses from N to P side, or an electron diffuses from P to N side. So while forming an PN junction diode, electron will be diffusing from N-type material and it will be cross over the depletion layer to recombine with the holes in the P-type material of the PN junction diode. Option A is the right answer. Next. Anode is a dash polarity in diode. So polarity is nothing but, that is either it is positive or negative. So in anode, it has the two terminal. One is in diode it has the two terminal. One is a positive terminal and negative terminal. Positive terminal will be called as the anode, and negative terminal of the diode will be called as the cathode. So anode is the positive polarity in the diode. So which of the following cannot move? As you all know that electrons are the majority carriers in the N-type material, and holes are the majority carriers in the P-type material. So holes also tend to move. The free electrons will also tend to move, cross over the barrier. Whereas ions will not tend to move. It is immovable ions in the depletion layer. So these ions cannot able to move from one layer to the other layer. What is a diode? Diode will be consisting of two terminals. Already I said one is positive terminal anode and negative terminal is cathode. While connecting the positive terminal anode to the positive terminal of the battery, as well as negative terminal cathode to the negative terminal of the battery, it will be under forward bias condition. It starts conducting the current, flow of current. So this diode will allows a current to flow in one direction. It allows current to flow in two direction, or it is a resistor. It will allows a current to flow in the one direction. That is the correct answer. Next. In the forward bias arrangement of a PN junction diode, the N end is connected to the positive terminal of the battery. The P end is connected to the positive terminal of the battery. The direction of the current is from N end to the P end in the diode. The P end is connected to the negative terminal of the battery. So many times we have discussed about this. Positive terminal of the battery is being connected to the anode terminal of the diode in the forward bias condition. Similarly, negative terminal of the battery is being connected to the cathode terminal of the diode in the forward bias condition. So in forward bias condition arrangement of the PN junction, the P end is connected to the positive terminal of the battery. What is the depletion layer region width? The depletion region width is micro by micrometer. As the doping concentration will be added more and more, the depletion layer region will be very, very thin. If the doping level is very, very lightly doped or very less number of impurities has been added to the improve the concentration, then the depletion layer width will be very, very thick. The peak inverse voltage for the full wave rectifier. The peak inverse voltage for the full wave rectifier is 2 Vs. In full wave rectifier, it will be connected in both the positive and negative cycles. It has been implemented the two diodes, diode 1 and diode 2. So the peak inverse voltage for the full wave rectifier is 2 Vs. The region which has large area and moderately doped is called. We have the three terminals in the transistor, one as emitter, base, and collector. So the another option is given as the anode. So in which layer the doping is moderately provided means that is called as the collector region. So the correct answer for this is collector. The threshold voltage for the germanium semiconductor is 0.7 volt, 0.3 volt, 1.1 volt, and 0.8 volt. So this we have already seen in the PPT slide, theoretical part of the PN junction diode. So 0.3 volt is the threshold voltage for the germanium and 0.7 volt is the threshold voltage for the silicon semiconductor. So the option 0.3 volt is the correct answer for this question. Which of the following is true in case of a forward biased PN junction diode? The four options are: positive terminal of the battery sucks electrons from the P region. Positive terminal of the battery injects electron into the P region. The negative terminal of the battery sucks electron from the P region. None of the above mentioned statements are true. So you have to keep this in your mind. In positive terminal of the PN junction diode, holes are the majority carriers, and in N-type region, electrons are the majority carrier. Under forward biased condition of PN junction diode, the positive terminal of the battery is being connected to the P-type P side of the diode. So it will gains the electron from the P region. So it sucks the electrons from the P region. So the option A is the right answer. Positive terminal of the battery will suck electron from the P region. Next. Sorry. Okay. Next is doping of semiconductors. So what is doping? Doping is nothing but process of adding impurities to improve the concentration of the charge carriers in both the p-type and n-type material. So the options given here are materials which can conduct electricity better than insulator, but not as well as conductors. The second option is the process of adding of a certain amount of specific impurities in the pure semiconductor. Last option is when 4 electrons in the outermost orbit. So the correct answer for doping of semiconductor is it's a process of adding impurities to improve the concentration of the charge carriers. As the level of doping is very high, the depletion region width will be thin. If the level of doping is very less, the depletion region layer width is thick. Next, what is the depletion region will consist of? Depletion region will consist nothing but minority carriers. It has positive and negative ions, no majority carrier. So the correct options are 2 and 3. It has the immovable ions, both the positive and negative ions. Depletion region between the PN and P-type and N-type material of the semiconductor, PN junction diode, it will consist of immovable ions or immobile ions of both positive and negative ions. It does not have majority carriers. So, as it does not have majority carriers, it will not allow the carriers to tend to flow of current because the charge concentration is very less. Automatically, the doping level is also very less. That's why the depletion layer region width will be very thick. In that case, it has only the immobile ions as well as the no majority charge carriers to conduct the flow of current. The region which is lightly doped and thin is called. So as you all know it very well, if the region is lightly doped, the depletion region width will becomes thin. So in that case, here we have emitter, base, collector and none. So we know that collector is the moderately doped level. So the region which is lightly doped is base terminal of the transistor. Next, when the diode is forward biased, it is equivalent to an off switch or on switch, high resistance, and none of the above. Surely it is not off switch because the diode is being connected in forward biased. So it will not offer any high resistance. None of the above options is also wrong. So what is the correct answer? When the diode is being under forward biased, it is ready to conduct the flow of current. So it is acts as an on switch. Next, the negative end of a diode is called. We know that positive end of the diode is called anode, negative end of the diode is called as cathode. So here the four options they have given: anode, cathode, pentode, and none of the above. So anode is the positive terminal of the diode and cathode is the negative terminal of the diode. So the negative end or negative side of the diode is called as the cathode. Next, in the Hall effect, the directions of both electric and magnetic fields are parallel to each other. Whether the above statement is true or false. Here the option is given as true or false. The correct answer is false. Why it is false means because in the Hall effect, the directions of electric field and magnetic field are perpendicular to each other. It is not parallel to each other. So the given statement is wrong. So it is option is false. If an external DC voltage is connected in such a way that the positive terminal is connected to the P region and negative terminal is connected to the N region, then the diode is said to be in. It's obviously they have given four options: forward, reverse, no, and forward and reverse. The correct answer obviously it is forward biased because here the given question is if an external DC voltage is connected in such a way that the positive terminal is connected to the P region and negative terminal is connected to the N region, then the diode is obviously it is said to be forward bias condition or forward bias direction. The displacement of the charges will result in magnetic field, electric field, rust or Hall effect. So the correct answer will be electric field. So the displacement of the charge will leads to the electric field. The region which is depleted of mobile charge carrier is called, the options are depletion region, potential barrier, both A and B, and none of the above. So the region which is depleted of mobile charge carriers. So mobile charge carriers with both the positive holes and the negative electrons, negative charge electrons. So it will be consisting of both the depletion region and potential barrier. The process of adding an impurity to an intrinsic semiconductor is called, options are doping, ionization, recombination, atomic modification. So doping is the correct answer, since it's the process of adding an impurities to improve the concentration of the charge carriers. If the Hall coefficient is negative, it is a which type of semiconductor? The options are P type, N type, intrinsic, extrinsic. So the Hall coefficient is negative, it is a N type semiconductor. Next. In off-wave rectifier, the diode conducts in only dash direction. So it will conduct off-wave rectifier. From the name itself, you can understand. Only one diode will be able to conduct, that too during positive half cycle only. So off-wave rectifier, the diode conducts only in positive direction. Next. Zener diodes are mostly used for, the four options are rectifier circuits, filter circuits, solar cells, and voltage regulator circuits. So Zener diodes are mostly used for voltage regulator circuits to regulate the flow of, regulate the voltage flow across the circuit. So for that we are using this Zener diode. The value of potential barrier for a silicon diode is, the options are 1, 2, 0.5 and 0.6. So the potential barrier voltage for the silicon diode is 0.6. And I left out two questions. We move on to the continuation with this circuit problems. In the given circuit shown, assume that diode D1 and D2 are ideal. In the steady state condition, the average voltage across 0.5 microfarad capacitor is. So here in this circuit, diode D1 and D2 are ideal. We have, under steady state condition, the applied voltage across the circuit is V is B. Now we have to find out the steady state voltage across the 0.5 microfarad capacitor is. We just redrawn the circuit as given in the figure. So during negative off cycle of the applied sine wave input, D1 is forward biased. We are applying KVL law, minus 50, because under reverse bias condition, forward bias, when the D1 is forward biased during negative off cycle of the applied sine wave input, minus 50 plus VC1 equal to 0 or VC1 equal to 50 volt. During positive cycle of input, applying KVL law, 50 plus 50 minus VAB equal to 0 and VAB equal to 100 volt. So the correct option is 100 volt. Next, in the circuit shown, assume that diodes D1 and D2 are ideal.
The average voltage of VAB in volts across terminals A and B is. The diode D1 and D2 are ideal as shown in the figure. We have to identify the voltage across the terminals A and B. During positive cycle of the input, D1 is forward biased and D2 is reverse biased. So the circuit will be reduced to like this. Now Vn equal to 6 pi sine omega t. VAB equal to 10k divided by 10k plus 20k into Vn. Now Vn by 3 equal to 6 pi sine omega t divided by 3, which is equal to 2 pi sine omega t. During negative cycle of the input, D1 is reverse biased and D2 is forward biased. Now VAB equal to 10k divided by 10k plus 10k into Vn, which is equal to Vn by 2. Vn is 6 pi sine omega t by 2, which is equal to 3 pi sine omega t. So VAB equal to 2 pi by pi plus 3 pi by pi, which is equal to 5 volt. The correct answer is 5 volts. Next. Assume that the diode in the figure has V on equal to 0.7 volt, but it is otherwise idle. Find the magnitude of the current I2 in milliampere is the given circuit can be redrawn as a Thevenin's equivalent circuit. It has been further drawn as equivalent circuit using Thevenin's theorem. Here the voltage across the diode is 0.5 volt, then the diode is off. The circuit reduces to like this. The current through the 6k ohm resistor is I2 equal to 2 divided by 2 plus 6k, 2k plus 6k, which is equal to 2 divided by 8k equal to 0.25 milliampere. 0.25 milliampere is the right answer. Next. Then diode D1 and D2 in the figures are ideal and the capacitors are identical. The product RC is very large compared to the time period of the AC voltage. Assuming that the diode do not break down in the reverse bias, the output voltage at the steady state is. Here, the diode D1 and D2 are given as ideal and capacitors are also ideal. The product time constant RC is very large compared to the time period of the AC voltage. RC is very larger than that of T, capital T. Assume that the diodes do not break down in the reverse bias. The output voltage at the steady state is. The solution is diodes D1 and D2 are ideal. The above circuit can be redrawn as like this as it is shown in the figure. During positive cycle of the input, D1 and D2 are shorted, thus V0 equal to 0 volt. During reactive cycle, the diodes are reverse biased, obviously V0 equal to 0 volt. Therefore, V0 equal to 0 volt at all the times. Next. The figure shows a half-wave rectifier with a 475 microfarad filter capacitor. The load draws a constant current I0 equal to 1 ampere from the rectifier. The figure also shows the input voltage Vi, the output voltage V0, and the peak-to-peak voltage ripple U on Vc. The input voltage Vi is a triangle waveform with an amplitude of 10 volt and a period of 1 milliseconds. Calculate the value of ripple in ripple U is. So here the given circuit is the half-wave rectifier circuit. Here filter capacitor equal to 475 microfarad. Load drawn constant current of 1 ampere. The input voltage is a triangular waveform. Output voltage Vc is given. One has to determine ripple peak-to-peak voltage. Amount of charge lost by the capacitor should be equal to the charge gained during the charging process. So time period T into IDE equal to Vt of peak-to-peak into C. So Vt of peak-to-peak equal to IDC into T divided by C, which is equal to 1 ampere into 1 into 10 power minus 3 divided by 475 10 power minus 6, which is equal to 2.1 volt. I hope so. You people have understood about the today's practice problems in PN junction diode and the Zener diode. I have started the classes with the introductory part of the PN junction diode. What is junction? What is PN junction diode? How the junction is being formed? What is depletion layer? What is doping? If the doping level of concentration is high, what will be the depletion region width, and if it is low, what will be the depletion region width? The total we have discussed. Then we have discussed about the advantages of PN junction diode along with the applications. Then we have come across the practice problems of this gate tutorial problems we have come across for your practice. I hope so you have understood it clearly. With this, I will wind up the today's session. We will continue with the next topic in the next class. Thank you all.